We have discussed what is to be done in circuit analysis. If you have a circuit with n nodes and b branches, we need to solve for 2 b variables, which consist of b voltages and currents in the b branches. Now, we saw that when the circuit has a single independent source, we do not have to resort to formal analysis. We can use series and parallel combinations of resistances to come up with a solution. Now, we will look at another method that is used before going on to formal circuit analysis. Now, this is known as using the principle of superposition to solve for circuits containing more than one independent source. Now, we have not yet proved the principle of superposition yet. Now, that will be very easy to do after we discuss formal methods of circuit analysis, but for now we will take it for granted and use the principle of superposition when we have more than one independent source. Now, it turns out that when you have a circuit with multiple independent sources, let me show the circuit like this. I will show all the independent sources outside, and within the body of the circuit, we will assume we will have only linear elements. Okay. Now, the linear elements are resistor, capacitor, inductor and also controlled sources. Now, in the initial part of the course, we will be looking at circuits without inductors and capacitors, that is circuits without energy storage elements. So, even these will not be there. So, essentially we will be discussing circuits with resistors and control sources. Okay. So, everything is enclosed in this except for independent sources, and of course, the condition is also that for these control sources, for these linear control sources, the controlling quantity is within this circuit. Okay. This controlled quantity could be dependent on some voltage within the circuit or some current within the circuit. Okay. So, we can't define, let us say, some other current flowing elsewhere outside the circuit and make this control source dependent on that. Okay. So, controlling quantity is within the circuit. Okay. Now, because these are all linear elements, it turns out that we can use the principle of superposition. Okay. So, we will call these linear circuits. Obviously, it means a circuit that consists of linear elements and independent sources. Okay. So, when we have such a circuit, let me take that example again. First, I will not worry about what is in the circuit, except to say that it consists of linear elements, and I will show independent sources like this. Okay. So, as I said earlier, what is inside this box? Those elements are all linear. Okay. Now, we know that these independent sources are not linear. Okay. We have discussed this earlier in the first unit, that the VI characteristics of these do not pass through the origin, they do not obey superposition, but what is inside this box? They are resistors and linear control sources. So, they are linear. Okay. And let me label these V1, I2, I3. Okay. Now, we have to be calculating for something in the circuit. So, I will highlight a particular voltage. So, let us say the voltage across this resistor. Okay. Now, what does the principle of superposition say? The effect of multiple independent sources acting together equals the sum of effects with each independent source acting one at a time. Okay. We will elaborate on what this means. In this particular circuit, there are 3 independent sources. What this is saying is, this VR, the voltage across the resistor, due to the 3 independent sources, can be calculated by taking one independent source at a time, calculating the value of VR for each case and summing the values together. Okay. So, that is all that is there to it. So, that is what superposition is. In other words, I have some VR here. Okay. So, instead of analyzing the circuit with 3 independent sources together, what I do instead is first analyze the circuit with only V1 being active. Now, what does this mean? This means that I set I2 to 0 and I3 to 0. Okay. So, what does it mean to set a current source to 0? When a current source is 0, we know that it is an open circuit. We have discussed this earlier as well. A 0 valued current source is an open circuit, because that means that no current flows between these two along this path. So, basically I have replaced them with open circuits. So, let me mark that here just for clarity. So, this is an open circuit and this is an open circuit. Okay. And let me call the voltage VR I get from this as VR1. Okay. So, what I do is the following: I set I2 and I3 to 0. So, I have now a circuit with a single source, and we know that this is quite easy to analyze, and from this I calculate the voltage across the resistor, or whatever quantity I want. If I wanted current through this source, I could calculate that. I am taking the resistor voltage as an example. Okay. So, I do this. Next, I analyze the circuit once again. Okay. This time I will have only I2 to be active. So, that means that V1 is 0 and I3 is 0. Okay. So, what do I do? I have to set I3 to 0. A 0 valued current source is nothing but an open circuit. Okay. So, that is what I do. So, I open circuit the current source, and I have to set V1 to 0. A 0 valued voltage source is a short circuit. Okay, because between these two nodes you have 0 volts. So, that means that we have a short circuit. Okay. And I get a certain value of the resistor voltage from this, and let me call that VR2. So, I calculate VR2. Okay. And finally, I do the analysis a third time, and this time I will have only I3 active, which means that I set V1 to 0 and I2 to 0. So, if I set I2 to 0, a 0 valued current source, we know by now is an open circuit, and a 0 valued voltage source is a short circuit. Okay. This is a short circuit, and the value of VR I get in this particular case, let me denote that by VR3. Okay. So, in this case I calculate VR3. So, there were 3 independent sources. I do the analysis 3 times. Each time I keep only one of the sources to be non-zero and all the remaining ones to be 0. Now, what does it mean? For voltage sources, setting them to 0 means replacing them by a short circuit. For current sources, setting them to 0 means replacing them by an open circuit. Okay. Then, for the full solution VR, I sum the 3 individual solutions VR1 plus VR2 plus VR3. Okay. So, this is how I can get the solution to the circuit, which contains 3 independent sources. Okay. Now, instead of analyzing one circuit, we did it 3 times, but each time with a single source. So, that is why it is easy to do, right. With a single source, it is always easy. So, we do it 3 times and sum the results together. Now, a couple of points I wish to make. First of all, sometimes when this is stated, students think of it as having only one source and removing others and so on. It is best to avoid such imprecise terminology as removing sources, etc. What we are doing is having only one of the sources to be non-zero and setting all the other sources to 0. Okay. And that makes it very clear that a current source should be replaced by an open circuit because 0 current, and a voltage source should be replaced by a short circuit because of 0 voltage. Okay. So, that is one thing. The second thing is, let us say you have a certain electrical quantity like the voltage across the resistor VR defined here. Make sure that you take it in the same polarity, in the same direction in every one of the analysis. Okay. In this particular case, the upper node is defined to be positive and the lower node is defined to be negative in the definition of VR, and that has to be preserved through all the 3 analysis. Okay. And in individual analysis, VR could come out negative or positive, whatever it comes out, you take it and then take the algebraic sum of all the results to arrive at the final answer. Okay.